So this is exercise 5Q and problem number 1. So let's see. We have a farmer that wishes to enclose a rectangular field of area 100 meters square. The farmer must buy fencing material for 3 of the sides, but the fourth side, one of the longer sides, will be an existing fence. So let's make a pause right here, guys, and let's already address this paragraph. Basically, what they're telling you is this: you have a fence already there, and what the farmer will do build will be building uh, an area, a field, right? He wants to enclose a field of this much area, and it's gonna do it in the form of a rectangle. So these 3 sides that I'm drawing right now in white, that's gonna be the fencing that he will be buying and applying in this area, because this yellow fence, it's already there. So he will not invest any money in this part. Okay, and we know that the area of this enclosing is 100 meters square. Then let's keep going. The shorter sides of the rectangular enclosure are to have length x. Okay, so these sides are labeled x, and let me label this z because I want to. And therefore this side should also be z. Okay, there you go. Now let's proceed with the questions. The question A says, write down the length of the longer sides of the enclosure in terms of x. So these are the longer sides, and I need to write z in terms of x. Well, that's very simple if we know that the area of the enclosure is x times z, and that is known to be 100. I'm going to ignore the units for simplicity. So we know that x times z equals 100, and that yields z being equal to 100 over x. So this is the longer side, z in terms of x. Okay, so A is done. Now B, find an expression in terms of x for the total length of the new fencing the farmer must buy to enclose the rectangular field. So I need to find an expression in terms of x for the total length. I'm gonna create that variable L for length, and what I mean is this side plus this side plus this side. That's gonna be the total fencing, the length of total fencing that he will be needing. So it's 2x plus z. But if you notice, this length it's given in terms of x and z, and the question is telling you to do it only in terms of x. So how do I replace this z right here? Well, with this one, right? All we have to do is 2x plus 100 over x. There you go. So now this is the total fencing needed in terms of x. So there you go. Now C, find the minimum length of fencing required and the value of x for which this minimum occurs. All right, so here's where the calculus starts to do its work, right? So you know that L is a function of x, and so I wanna do this, guys. I wanna say that L is a function f of x, and that function is 2x plus 100 over x. So we have this function, right? And given all the work that we did in the previous week, we can actually find, the critical points, the turning points, if there are any, and so on. So let's find out whether this thing has a turning point, and let's see if that turning point happens to be a local minimum, right? Because that's what we need. We need this function to be a minimum. So let's see. Let's find the critical points of this function f. So let's go over here. We have the function And as we know by now, we have to get the derivative of this function. So that's going to be 2 minus 100x to the square. You know how to do this already. I'm not going to be giving you the details of the derivatives. So this is the derivative. And in order to find the critical points, I need to make the derivative equal to 0. So I need to write this. There you go. And then solve this equation for x. I am multiplying by x squared in both sides in order to produce this. And the rest is very simple. I'm gonna take some shortcuts as always. You do the rest, right? So we have two accepted values for x, which is the positive and the negative square root of 50. But obviously, given the context of the problem, the negative value is inadmissible, right? Because there is no such thing as negative sides. So the only acceptable solution for x is the positive square root of 50, which is about 7, right? Okay, so this is the critical point. The critical point for this function happens at x equals the square root of 50, which is pretty close to 7. All right, now, how do I know that this critical point is in fact a turning point? And furthermore, how do I know whether that's a minimum? How do I know that? How do I know that? Well, we can find out with the second derivative test. Test of the second derivative. And what we need to do is basically get the second derivative of the function. If this is the first derivative, I'm gonna differentiate again, and you will be getting 200 over x to the 3. If you differentiate this function, you will be getting this. And then you need to evaluate in the critical point, which is the square root of 50, and basically just notice the sign of the result. So the sign obviously will be positive, right? 200 over the square root of 50 to the cube, that's going to be positive, which is greater than 0, and therefore the point is a turning point, and it is a minimum, a local minimum, and as well as an absolute minimum in this case. All right, so that's it, guys. That's your solution. The minimum length of fencing required happens when x is the square root of 50, right? And therefore, all you need to do next is basically input that value in here, right? So I'm going to do that in yellow here in order to avoid confusion. The minimum length will be L equals 2 times the square root of 50 plus 100 over the square root of 50. This is the minimum length required, and that happens when x is the square root of 50. So there you go. D. Sketch a graph of fencing length against x to confirm your answer. So basically, guys, just grab your TI or Desmos, input this function, and you will see that its minimum happens when x is exactly this value. All right, so that's how we can minimize the length of this enclosure, and it finishes this problem.